In this video, we discuss long-run production, where all inputs are adjustable. To model two inputs into the output, it is very useful to have a production function. A common production function used in many applications is the Cobb-Douglas production function. With two different inputs, we can write Q is equal to A times L raised to the power of A, and the amount of capital K raised to the power of little b. This is very similar to the familiar Cobb-Douglas utility function. It is basically the same functional form, where the lowercase a and b are just constants. Just like the Cobb-Douglas utility function that can be plotted in a 3D graph as a utility hill, this production function can also be plotted as a production hill, where the coordinates of the two inputs correspond to an altitude on the hill that represents the level of the output. I'd like to point out that despite the similarities, there are two important differences here from the utility function. First, little a and little b here don't have to add up to 1. We will discuss their implications a little bit later. Second, there is sometimes a constant, big A here, multiplied to the product of L and K. This is just a value that rescales the output in ways that are independent of the inputs. You can think of the production hill as a big inflatable surface that can be blown up or shrunken down by this parameter of A. Economists use this parameter to capture the differences in the output that are not explained by the inputs. For example, if two firms use very similar measurable inputs, but one produces more output than the other, then one firm has a higher big A than the other. This parameter A is called the total factor productivity. You probably will see this term in the Solow model in the macroeconomics courses. When we're primarily interested in the role of inputs, we can ignore this constant of big A and simply write the output is equal to labor raised to the power of little a and capital raised to the power of little b. By doing this, we're just counting the outputs by groups of A units. The Cobb-Douglas production function is widely used in applications. For example, Xie 1995 models the output of a US electronics firm as a Cobb-Douglas function and estimated the parameters little a and little b using data. He found that in this context, little a and little b are both approximately 1/2, which means both inputs contribute to the outputs at about the same rate, so they're equally productive. Because we use production functions to model how the two inputs map into the output, it is useful to understand the substitution patterns between these inputs, so that if we need to produce a particular amount of output in our model, we can start to think about how to optimally choose the combination of inputs. Just like we can use indifference curves to understand the combinations of goods that deliver the same level of utility, here we can use very similar curves to describe the combinations of inputs that deliver the same level of output. We call this curve the isoquant. ISO stands for equal and quant stands for quantity. Very similar to the indifference curves, we can define the isoquant as the combinations of inputs, L and K, whose outputs are equal to a particular level of a constant Q bar. Their mathematical properties are exactly the same as the indifference curves. You can see that the graphs of the isoquant look very much similar to the indifference curves. Similarly, all the properties of the indifference curves must also hold for the isoquant. All the isoquants will be convex. All the isoquants towards the upper right corner will represent a higher output level than those that sit down below. The isoquants will not cross each other, and the isoquants will all slope downwards. And lastly, isoquants will have to be thin, so you will not have 2 points sitting right next to each other on the isoquant, but one sits towards the upper right corner of the other. Moreover, just like the indifference curves, we can also think about different types of isoquants in extreme cases. When the inputs are perfect substitutes, the isoquants will be perfectly straight. When the inputs are perfect complements, the isoquants will be angled at 90 degrees. And usually, most isoquants will behave somewhere in between of these two extremes. So the two inputs can substitute each other, but not perfectly. Also, just like the indifference curves, the slope of the isoquants that represents the substitution pattern between the two is a very important object for the firm's choices. We're going to call it the marginal rate of technical substitution, or MRTS. The word technical is here to differentiate it from familiar notion of marginal rate of substitution for indifference curves. The interpretation of the MRTS is the amount of input on the y-axis that we can replace with one additional unit of input on the x-axis, given that we have to produce exactly the same amount of output. The mathematical expression for the MRTS is defined as the marginal product of the input on the x-axis divided by the marginal product of input on the y-axis, and with a negative sign in front. Again, exactly the same idea as marginal rate of substitution. The derivation is also mathematically equivalent with some very small changes in the notations. For example, in the graph here, we have labor on the horizontal axis and have capital on the vertical axis. So the MRTS is just the marginal product of labor divided by the marginal product of capital with a negative sign. Now let's look at a simple example that calculates the MRTS for Cobb-Douglas production function, where the powers on L and K are both 1/2. Just like calculating marginal rate of substitution, we first calculate the derivatives, or the marginal products, for each input, and then we'll take the ratio and put on a negative sign. So the marginal product of labor is the derivative of the production function, or this one, with respect to L. So the derivative will give us 1/2, which is coming from the power on L, times K over L raised to the power of 1/2. The algebra is exactly the same as the example where we calculated MRS for the Cobb-Douglas utility function. And similarly, the marginal product for capital is just 1/2 times L over K to the power of 1/2. And once we take a ratio between these two marginal products and with a negative sign, we can find that the MRTS is just minus K over L, which takes a very similar form as the marginal rate of substitution. Because the isoquants are convex, so they exhibit a diminishing marginal rate of technical substitution. This means that as we increase the amount of input on one axis, it will be able to replace less and less amount of the other input. Here we see that on this graph, the absolute value of the slope of the isoquant decreases as L increases. And similarly, going the other way, as we increase the amount of capital we use, the amount of labor it can replace becomes less and less and less. Overall, our model of the production function is very similar to the utility function. So, except for the interpretation, all the mathematical structures translate very well to isoquant. Now, let me turn to discuss a property of the production function that we have not mentioned before, which is the concept of return to scale. When we discussed short-run production, we talked about the idea of diminishing marginal returns. And we motivate the concept using thought experiments where we keep doubling the input we can adjust in the short run. We said that because the size of the garden or the windowsill is limited, so up to a certain point, doubling all adjustable inputs just won't double the output. But you may wonder, in the long run, If we can adjust all inputs, such as building a different garden, would we be able to double the output then? Well, in fact, we can ask an even more general question, which says, if we double all the inputs in the long run, what will happen to the output? Will the output double, or less than double, or more than double? In other words, with our production function, we can check the output we get when we double the amount of inputs against twice the amount of good that we would have gotten before the inputs were doubled. For example, if using 1 unit of labor and 1 unit of capital, I produce 3 cupcakes. Now, I can compare the output I would get when I used double the amount of inputs against twice the amount of output, which is 6 cupcakes. If I can get more than 6 cupcakes by doubling the inputs, we say the production function exhibits increasing return to scale, meaning that as we increase the scale of production by doubling the inputs, the output grows at an increasingly faster rate. Similarly, if by doubling the inputs, we get exactly twice the amount of output as before, then we say the production function exhibits constant return to scale. The last remaining scenario is that by doubling the inputs, the amount of output we can get is less than twice the amount of output we got before. Then, in this case, we say the production function exhibits decreasing return to scale. Now let's take a look at how these cases will look graphically. We can illustrate the return to scale using different isoquants. In this graph, the firm in the model produce 100 units of output when they use 100 units of input for each labor and capital. When they double the inputs, the output reaches the isoquant that's exactly twice the amount of output, which is 200 units. So we have a case of constant return to scale. In this next case, just like the previous one, the firm produces 100 units of good when they use 100 units of input for each labor and capital. Now, as they double the input to 200 and 200, the output reaches isoquant that represents an output level of 142, which is less than double the output of 200. The isoquant for double the amount of output is way up here, and by doubling the inputs, they cannot reach all the way up there. So in this case, we have decreasing return scale. In the third case, we start from 100 and 100 units again with an output of 100 units. But now by doubling the inputs, the output we can get is actually 239 units, which is more than doubling the amount of outputs. So in this case, we have increasing return to scale. So the graphs are quite intuitive, but how would these properties look algebraically when we have a general Cobb-Douglas production function? Here, the production function takes a Cobb-Douglas form with the total factor productivity A in front and with powers on labor and capital being little a and little b. Now let's try to calculate the output we will get when we double the inputs. If we double the inputs from whatever level they started with, L and K, to twice as much, which is 2L and 2K, then the inputs just becomes 2L and 2K. In other words, we're just changing the value we feed into each one of these slots for L and K to 2L and 2K. And that's exactly this function we have here. Then we can isolate this 2 to the power of A and 2 to the power of B and combine them. Once we do that, we get 2 to the power of A plus B in the front, and then the remaining term just becomes exactly the same production function that we have before doubling the inputs. In other words, when we double the inputs, the output we get will be 2 to the power of a plus b times the output we got before the inputs were doubled. And now let me ask, when does this function have increasing or decreasing or constant return scale? Can you pause the video here and think about the question from the expression that we just derived? Please give it a try. All right. First, let's see when we have an increasing return to scale case. We know from the previous expression that when we double the inputs, the output we get will be 2 to the power of a plus b times the amount of output we get without doubling the input. And if the output level is greater than twice the amount of the original output, then we have increasing return to scale. But notice that this entire term of f of L and K are exactly the same on the left-hand side and right-hand side of this inequality. So it can just cancel out. And because this is a positive value, which is just the amount of output, when we cancel out these terms, the sign of the inequality does not change. So this inequality is equivalent to 2 to the power of a plus b is greater than 2, which is equivalent to the power, a plus b, is greater than the power, which is 1 here. So in other words, we will have increasing return to scale if and only if the sum of the powers on labor and capital add up to be a value greater than 1. And similarly, the same reasoning holds with the opposite inequality sign or an equality sign. And those cases will lead you to the decreasing return scale case or constant return scale case. In other words, when the sum of the power on the two inputs are less than 1, we have decreasing return to scale. When they add up to 1, then we have constant return to scale. The takeaway from this example is that the Cobb-Douglas production function has a very nice feature, that the sum of the powers on the inputs corresponds to different returns to scale. This return to scale has nothing to do with the level of inputs L and K, or the total factor productivity, capital A here. This may be a somewhat restrictive feature, but it offers a very nice way to interpret empirical evidence from data. Many studies assume a Cobb-Douglas production function and try to estimate the parameters of little a and little b from data at the firm level. With the result we just derived, we can interpret these parameters with intuition. For example, the studies found that in US tobacco products, in Bangladesh glass, in Danish food and beverages, and Chinese high technology, the empirical evidence found that the scale parameters add up to be less than 1, meaning in these industries, they have decreasing return to scale. For some other contexts, the evidence shows that the scale parameter add up to be approximately 1. For instance, in Japanese synthetic rubber, Japanese beer, New Zealand wholesale trade, Danish publishing and printing, then in these cases, we interpret it as the industries are having a constant return scale. And in some contexts, the evidence found a scale parameter to add up to be greater than 1. Then in these cases, we think these industries have increasing return scale. It is worth noting that the feature of the Cobb-Douglas function, that the return to scale does not vary with the input level, is potentially restrictive and can be unrealistic. This graph illustrates how the return to scale may change as the input increases. In this graph, from the input level of 1 and 1, we have an output level of 1 unit. Now, when we double the inputs to 2 and 2, the output level more than doubled and went from 1 to 3. In other words, when we move from point A to point B, we actually have increasing return scale. What if we double the input level from 2 to 2 again to 4 and 4? Well, in this case, the output doubled exactly from 3 to 6. So when we move from point B to point C, we actually have constant return scale. Now, what if we double the input again from 4 and 4 to 8 and 8? Then in this case on the graph, the output is less than doubling. It's only going up from 6 to 8. So in other words, as we double again in terms of inputs, the output is less than doubling, so we have decreasing return scale. If we think of the situation in the graph as a more realistic representation, where the return scale can actually change around when the level of inputs change, then we can interpret the results on the previous slide about all these different industry studies as a reflection of the state of those industries when they're operating at that time. From those estimates alone, it is difficult to know how the return scale may change when their input levels change dramatically. To understand that, we will need more sophisticated models and perhaps more data. The properties of the production functions have important implications in estimating productivity at the firm level, and they are critical for modeling the firm's cost.